In these slides, we will be talking about content-based recommender systems. Some acknowledgements about the content of these slides are in order. We'll be talking about a different kind of recommenders. So far we have talked about collaborative filtering, whose distinguishing aspect is that it is solely based on identifying patterns from the collective behavior of users in the system. In content-based approaches, there is no collective aspect. No collaboration takes place. All recommendations for a user are based on the user alone, and other users do not influence them. Still, there is feedback history. That is, for each user, there exists a set of items interacted, rated, clicked, purchased, etc. with. Similar to item-based collaborative filtering, the system recommends items similar to those the user has liked in the past. However, unlike item-based collaborative filtering, the similarity is not determined from the ratings of other users. Instead, it is solely determined on the content of the items. Here, content means any description of the items, be it in terms of product features or unstructured text. So let's discuss some terminology. As discussed, the item content is an umbrella term for all the things we know about what an item is. There are different ways to define the content depending on the domain. Conceptually, creating the contents of items is the task of the content analyzer. The other important term is the user profile. This is a description of the user's preferences made in terms of the item content. Conceptually, the user profile is created by the profile learner, which aggregates the item content in the feedback history of each user. Again, there are different ways to achieve that. And the last important concept is that of matching. A content-based recommender estimates how well the user profile matches the content of an item. This task is the responsibility of the filtering component. As always, different methods for matching exist. To visualize the process of making content-based recommendations, we can relate to this figure. Observe the three main components of the recommender which we have introduced: the content analyzer, the profile learner, and the filtering component. The flow starts from the bottom left corner, where information about items is analyzed to create a structured representation of items. This is a one-time process that executes whenever a new item appears in the system. Henceforth, these represented items is how the system sees the items. The next important flow concerns the second component, the profile learner at the middle top. It takes as input the historical information about a user, which consists of two elements: the content of the items interacted with and the associated feedback. Here, the item content is the processed internal representation of items in the system. The output, of course, is a profile of each user in terms of item content. And the last important component is filtering. It takes as input the user profiles and the items representations and produces a list of recommendations for each target or active user. Once the user interacts or gives feedback about an item, the loop closes, as this feedback in turn affects the user profile. In the following, we will examine the three main components in detail, presenting some typical ways to implement them. We start with the item content. Well, we have said that almost anything can be considered as the content of an item. What is important is that we have the same level of description for each item. The same set of attributes or features are available for all items. These attributes can be structured like price, type, or category, and attributes can also be non-structured, like text, for example. This table here shows 3 items which are books. They are described by 5 attributes: genre, author, type, price, and keywords. This table is all the information we have about items. However, this information is often not suitable for our purposes. Remember that at the end, we will be creating user profiles from item contents, and then we will be matching them to item contents. So we need a more convenient internal representation that we can manipulate arithmetically. The simplest representation is in terms of vectors. Each item will be henceforth viewed as a vector. This has the important advantage that we know how to aggregate vectors and how to define similarity between vectors. Remember that in collaborative filtering, we have been treating items as vectors the whole time. In memory-based approaches, an item is a vector of user ratings. In model-based approaches, an item is a dense embedding learned from the history of user-item interactions. So it seems we like vectors, and for obvious reasons. Okay, so how do we get vectors out of the content of items? Well, for some attributes, the conversion is straightforward. For example, for numerical attributes like price or categorical like type. For others, particularly the non-structured attributes like set of keywords or genres and text, we have to resort to information retrieval techniques. We will next cover some basic ideas for these types of attributes. One important concept is the so-called vector space model. The goal is to convert a non-structured attribute like text into a vector representation. For this discussion, we will be using the information retrieval term documents to refer to one such attribute. For the context of recommenders, our goal is to create a vector for each attribute. Then we can concatenate the vectors for all attributes to obtain a vector representation for the whole item. So, for the next few slides, we will be talking about documents. And a document is represented by an n-dimensional vector where n is the number of terms or the dimensionality of our representation. Each coordinate of the vector is the weight WTD of the term T for the particular document D. We will describe a simple method to create the vector representation of documents. In what follows, we will discuss 3 steps for converting a document into a vector. First, we assume bag of words semantics, and briefly this means that each term of the vector corresponds to a word in the language. Then we will count the frequencies of words, and finally we'll be computing weights from these frequencies. We note that this document representation is going to be a very sparse vector, as there can be many words in a language, whereas a document, especially a short one, may only have a few of them. We note there exist more modern approaches based on representation learning that derive dense embeddings for each document, but we will not be reviewing them here. Okay, so let's start with step 1. We consider a document as a bag of words. This means that a document is just viewed as a multiset of words where their order is not relevant. This implies that the document that says John is quicker than Mary and the document that says the opposite, that Mary is quicker than John, are identical, as they contain the same words and in the same frequency. So this may seem restrictive in general, but in practice it serves its purpose of capturing the general meaning of the document. And this is often all we need for when we encode item attributes like movie genres or plot keywords into a vector. The second step is to count the frequencies of each word. Consider an example with 6 documents that are plays by William Shakespeare. These plays are the columns in the following table. For this example, we will be focusing on just a few of the possible words in the play, these 7 words shown as rows in the table. For each play, we count the number of appearances of each word. This is the number shown in each cell of the table. Then, a document like the Julius Caesar play is represented as a frequency vector, a column in this table. The last step is to adjust or normalize these frequencies. And here's why we need to do this. Think about this question. Does the frequency of a word really represent its significance in the document? So we see 2 problems with the raw frequencies. First, the significance does not increase proportionally with frequency. For example, a document with 10 occurrences of a particular word is more relevant for this particular word compared to a document with a single occurrence of the word. So this is clear, but saying that it is 10 times more relevant is probably not true. The second problem is that the significance of a word should consider the overall frequency of a word in a collection of documents. For example, a very common word is not that significant compared to a less common word just because it appears more often. And this is exactly the case of stop words like articles, which appear many times in a document but carry little information. To address these 2 problems, we will transform the raw frequencies into appropriate weights. The weight WTD of term T in document D will be computed as the product of 2 terms. The first term, TF of T in D, is called the term frequency and addresses the first problem. The second term, IDF of T, is called the inverse document frequency and solves the second problem. Together, this approach is called TF-IDF in the information retrieval literature. And let's see how it works. First off is term frequency. So a little historical journey here. Gustav Fechner was a German philosopher that studied the relationship of mind and matter. Specifically, he theorized how variations of a physical quantity, like the intensity or energy of a light source, caused variations in the perceived subjective experience of a human, like how bright the light is perceived. He proposed that in many cases, the connection between the physical quantity and the perceived quantity is logarithmic rather than linear. So what this means is an increase of stimulus intensity by a given factor, say 10 times, yields the same constant increment on the personal psychological scale. So in our setting, if the frequency of a term increases from 10 to 100, the perceived increase in significance is similar to the case where the frequency increases from 100 to 1000. Let's put this idea in practice. The term frequency of a term is computed as 1 plus the logarithm of the raw term frequency. When the raw frequency is 0, the term frequency is set to 0, as in that case the logarithm is not defined. If the base of the logarithm is 10, we have the following examples of raw frequency converted into term frequency. 0 becomes 0, 1 becomes 1, then 10 becomes 2, while 1000 becomes 4, meaning that the term encountered 100 times more is only 2 times more important. Okay, now for the second term, inverse document frequency. The main idea is that rare terms in the whole collection are more informative than frequent terms. We have already said that stop words like articles carry almost no information. In contrast, a rare item like the word trypophobia is very important. We would like to reward such infrequent terms. So here's how we do this. The document frequency dft of term t is the number of documents that contain t. This means that the less frequent the term is, the lower its document frequency. Recall that we actually want to reward small values of document frequency. That is why we inverse it. The inverse document frequency, or IDF, is given by this formula where n is the number of documents. Here we take the log of the normalized inverse of the document frequency. One thing to note is that IDF is defined for a term independent of documents. Let's see an example of IDF. Suppose we have a collection of 1 million documents and we investigate the IDF for the 6 words shown in the table. The term Calpurnia is extremely rare and it appears in one document only. That's its document frequency. As a result, it has an inverse document frequency of 6. In contrast, a stop word like the is naturally very popular and appears in all documents. Hence, its frequency is 1 million, but its IDF is 0. We see in this table how the popularity of words is transformed into IDF. As we said before, in TF-IDF weighting, the weight WTD of term T in document D is the product of its TF with IDF. Putting the definitions of TF in IDF, we end up with the following weight. Notice that the weight is high if the number of term occurrences in the document is high, in the TF part, and if the number of total documents that have this word is low, the IDF part. In this example here, we see the raw frequencies and then how they are turned into TF, IDF weights. We will now talk about the other 2 parts of a content-based recommender, creating user profiles and doing the matching with item contents. In general, this problem can be seen as a classification task. Decide whether an item content matches the user profile, that is, determine if this item is relevant for the user or not. In the following, we will discuss 2 ways to construct user profiles and do the matching: k-nearest neighbors and relevance feedback. Okay, first, This approach is actually as similar as it gets to item-to-item collaborative filtering. The only difference is the similarity computation. CF compares rating vectors, whereas here we will compare item contents. In this approach, the user profile is the set of vectors for all past rated items. Then, matching is performed by comparing the vector of the target item with each vector in the user profile. We compute a similarity score, and then we take the weighted average of the rating, where the weight is the similarity. But which similarity function will we use? Where Euclidean distance is a bad idea, and we show it with an example. Suppose we have the target item Q shown in the 2D space as a vector. Consider three other items, D1, D2, and D3. Which one is closer to Q? Well, in terms of Euclidean distance, D1 is closer. However, take a look at item D2. It is a longer vector, probably because the description of this item is longer, that is, it has more terms. However, note that the distribution of the weights in this item D2 is similar to the distribution of terms in the target item Q. We know this because the direction of the two vectors is similar. So we probably want to say that D2 is more similar to Q than the other two items. Let's do a thought experiment to understand how to think about similarities in the vector space. Consider an item with vector D and append its description to itself to create a new item with vector D prime. So semantically, D and D prime are identical, they have the same content. The Euclidean distance between these two items would be quite large, failing to capture the semantic similarity between them. However, if we look at the angle between the two item vectors, we find it to be 0. So this probably means that the angle is a better measure of semantic similarity. Here's something else to think about. What if we normalize all vectors to have unit norm? Then they would all lie in a hypersphere. Would the Euclidean distance be able to capture semantic similarity then? Well, the answer is yes. Okay, let's return to the fact that the angle captures the semantic similarity between the two vectors in the vector space model. Instead of the angle, it is easier to compute the cosine of the angle, giving us the cosine similarity, computed as shown in the formula for a target item Q and the past rated item D. Recall that each coordinate of the vector is the TF-IDF weight of a term. Also, it is convenient to know that if the two vectors are normalized, then denominator takes the value 1, and cosine similarity becomes the inner product of the two vectors. We are now able to present a rating prediction for the k-neighbors content-based approach. For a target item Q, determine the k-neighbors from the user profile. Then, compute the similarity weighted average rating among the k-neighbors. Here's the formula. Does it look familiar to you? So we already said that it is similar to the item-based collaborative filtering idea. Okay, so the other content-based approach we will discuss is called relevance feedback. The idea comes from information retrieval in that users feed back into the system the relevance of retrieved documents. Specifically, we will be talking about Rocchio's method. Here, the user profile is a single vector that is a linear combination of the vectors of the past rated items. And this is the main difference with k-neighborhood approach where we preserve the vector of each past-rated item. Matching is done similarly by computing the similarity of the target item to the user profile. Let's see how the user profile vector is built. First, we note that the past-rated items are split into two classes, those with a positive feedback, D+, and those with a negative feedback, D-. The user profile is a linear combination of three components: some baseline vector, a prototype for the positive, and a prototype for the negative class. So what are these prototypes? If we look at the figure, we see a number of vectors for positive feedback represented as circles. The average of these vectors, their centroid, is the prototype for the positive class. Similarly, the negative feedback is represented as crosses, and their average is the prototype for the negative class. Intuitively, the prototypes summarize the two classes. Then, the user profile vector is given by this formula. It takes into account a baseline vector, which can be some prior user preferences, and the two prototype vectors shown in green and red. These three components are weighted by three parameters, alpha, beta, and gamma, whose value are set manually, for example, after some validation. The last thing to discuss about relevance feedback is matching. Well, this is simply done by computing the cosine similarity of the user profile to the target item. This cosine similarity represents the expected degree of interest or relevance of the user to the target item. Let's finish by discussing content-based approaches in general. First, some benefits. There exists user independence in that the ratings from other users are not needed and do not affect the recommendations. Moreover, we have no cold start problem for items. Their relevance is only determined by the item content, and no previous feedback on the item is required. This means that content-based recommendations can work for dynamic items that are generated on the fly or have not been seen before. By the way, is there a cold start problem for users in content-based approaches? What do you think? And the other benefit is transparency, as recommendations can be explained by simply listing the items a user has previously liked. In terms of drawbacks, we mentioned that content-based approaches might not work for all domains. In general, you need to have good features, which can be hard or even impossible to get, like in movies or music. Another problem is over-specialization, which is also the case with item-based neighborhood approaches. The user gets recommended only similar items to those already rated. The user gets more of the same and may be trapped in the so-called filter bubble, where there is little or no novelty and serendipity, the possibility to be positively surprised by a recommendation. And the last drawback is that content-based approaches require some feedback in order to make recommendations.